You ready to start?
Yes.
Yeah. This is live streaming here also, so I have to stand above here, I think. Yeah. So everyone, welcome. This day's dissertation ceremony starts with this trial lecture. It's him, Pierre-Marie Lefeuvre. His trial lecture is on the title Subglacial Processes and Subglacial Hydrology.
I have to start with that, make sure everything good. So, I was given this topic for my trial lecture, the processes that control glacier sheet erosion rates. And today, so we're going to explore a bit of the Norwegian landscape and why did we have in Norway these very nice U-shaped valleys, and what has happened to this area is caused by glacier erosion. This is a part of the Alaskan southern range, and what's important to see is this plume of sediments here. So it's to show that when glaciers are eroding, all these white-water glaciers, it's not only that they erode and affect just the landscape, they also produce a lot of sediments that will affect not only where you have glaciers, but way further south. This plume is 100 kilometers long, so it will affect the marine ecosystem, the coastal ecosystem too. So today, we're going to start with an introduction. Why is erosion? Why is it important to study it? And then we will look at the different erosion processes. So the most known and most dominant processes occurring below the glaciers and ice sheets are abrasion and quarry. Then we will look what happens when we have sediments below glaciers and how they are eroded. It will be ice thrusting. And then we look at an interesting phenomena where you have dissolution of the rocks and the glaciers, so looking at chemical weather. And then in the third part, we are going to look at the controls of erosion rates, the geology, rock hardness, for example, and then the ice dynamics, and a kind of recent topic that has been studied is the subglacial hydrology. How does it influence the erosion rate? And then I will conclude. So you see again these plumes of sediments coming out of the glaciers. Erosion. So what is erosion? Erosion is the removal of a surface material from the earth first. So, and the glaciers is primarily rocks or sediments, and they are transported away from the point where they were. So this can be either mechanical erosion, so mechanically removing, breaking down the rocks, or chemically eroding the rocks, which means that you dissolve some elements of the rocks, some minerals, in water. So this is one example. You have a schematic version of a glacier here, and then you have the bedrock below. And what we're going to look at is the abrasion here, caused by the glacier movement. We will see it a bit later, and this is also showing plucking. Interestingly, we will look also at what are these glaciers left behind when they retreated, and they cause this landform called motion today that I will present to you right now. But let's talk about the importance of erosion rates and glacial erosion. I mentioned that they produce a lot of sediments, and these sediments can affect, by understanding glacial erosion, we can look also at the marine ecosystems close to glaciers. Here what you have is an iceberg with a lot of small seals, and this is in front of a glacier, and all around in this water you have this dark plume filled with sediments, full of sediments. And the sediments are giving kind of the first nutrients for the marine food chain, so phytoplanktons that attracts fish, that attracts the seal. So we can look at the whole ecosystem through that. The other part, maybe the most studied one, is the landscape evolution. By looking at erosion, we can more understand why do we have, for example, such an alpine terrain in the Himalayas and so low terrains in Norway. Obviously, so this mountain building is a balance between tectonic uplifts and erosion, and glaciers play a key part in this erosion. So let's continue on this. How do we form mountains and the importance of glaciers? Glaciers are called, the effect of glaciers is called glacial burst sow. Burst sow is this circular sow that is used to cut wood, and it's used, this word is used because they are so efficient at eroding, and they are thought to control the maximum height of mountains. What you have here is a figure from Brockett in the 1990s. You have the altitude from 0 to 8,000 meters, and then you have a cross-section along the American mountain range. So from the North Pole to the equator, and then down to the South Pole. And what you can see here is the profile with all the mountain range, you get the maximum elevation, and you have this very important line, this black line, and this represents the snow line. And the snow line elevation, where do you transform so precipitation from liquid to solid, is controlled by this latitude and also this elevation. As you go higher, it's colder. As you go further north, it's also colder. And it seems to follow, this line seems to follow the maximum height of this peak. And it is so that because of this snow line, we have also more glaciers. And so when you go above, you form glaciers that will erode much more and will stop mountains to grow above, too far above this line. So that's an important concept for erosions. Another important thing for erosions is that they are way more efficient than fluvial processes at eroding rocks. So for one important reason, if you look at the cross-section of a glacier, and if you look at the cross-section of a river, the glacier will erode all along its bed at the interface between the ice and the rock, whereas rivers will only erode at its lowermost point. This is a figure showing the erosion rate and the basin size. So that's why we have to relativize a bit, because this triangle here show glaciers erosion rates, measures, observations. And you see that they are actually a bit higher than these dots here, circles. Circles represent erosions from rivers. And what you see, they are a bit higher than these basins, but they also are eroding much smaller basins. So it's because they are closer to the mountain than the rivers. So an important thing is they erode more, but they also erode at much smaller bases. Then, although they are at very small places, their glaciers and ice sheets have covered a much larger range, much bigger parts of the globe. So I will show you now a video showing, so you have the date here, the video showing the ice extent from present to the last glacial maximum. So we're going to go backward in time. And so what you see is the ice was actually, due to climate, the ice was much further down and was even reaching France at some point. Then we can look, another thing is this ice, not only affected where the continents that it was covering, but also affecting all the lands further south because of the sediment production that I mentioned earlier. We can look at this problematic in a kind of source to sink system. So we have this erosion, the processes, and we mostly understand them by looking at erosional landforms. So when the glacier retreated, they left a lot of rocks that were shaped as the glacier. So if we understand the shape, we can understand the processes. and that's the main basis for what I'm going to talk about later. And from this, we developed some theory, and some people have been trying to do some modeling and some experiments, trying to justify and test a bit this theory. An important part is the transport, so from where the sediments were eroded to the deposition, and that has been giving a very interesting wealth of data, because you can monitor the front of glaciers, there is these rivers, and you can monitor the sediment concentration, and this gives you an idea of the how much sediments they eroded. So the volume, and you can relate the volume to these processes. Can these processes produce so much sediments? And the other parts, which brings us even so at another time scale, looking even further back in time, we can look at long-term erosion variations or erosion rates. By looking at the sediment thickness in fjords, for example, in the sea, and we can try to date different layers and then try to obtain the erosion rates. And I will present some of it during this lecture. We have just one problem, is depending on what you're looking at, we don't obtain the same erosion rates. So these are erosion rates from the Northwest Pacific, so Alaska, this American mountain range. So we have Alaska, Patagonia, and Pacific Northwest coast mountains. And you see that these erosion rates here, the value changes depending on which time scale you look at. So do you look at a couple of years, or if you look at hundreds or tens of thousands of years? And so that's what we're going to try to explore, because these erosion rates vary, have changed, and it depends also by the methods you're looking at. So this data here comes from these measurements at the glacier fronts in these rivers. But here we are looking at sediments that were deposited in the fjords. So there is some problems to reconcile all of this. So let's look at erosion processes. We're going to look at what's happening below the glaciers. And this landscape that you see here, two pictures, were below the ice before, and there are evidences for that. You see here long striations following, long striations, and perpendicular to that, you have these surfaces. It seems that there is a block missing. And this is, you have to consider that they are different scale. This is a small scale, this is a large scale, but it's the same processes. And what seems to happen is the glaciers have been grooving and plucking off some of the rocks. The other thing is, you can even look at a larger scale, because glaciers form, as we've seen at the beginning, large parts of fjords, valleys, and we can try, by looking at these erosion processes, we can try to reproduce this landscape. So what you have here is you have these U-shaped valleys, these crests, and then you have these valleys that are hanging. So it's called hanging valleys because they are separated from the main trunk by very steep cliff. And what you can also not see here, but you also have overdeepenings. So very deep trough filled with sediments. So we're going to look at that. The first process, the one that has been studied the first, is called abrasion. So abrasion occurs when you have this ice, and the ice will abrade the bedrock, because at its base it contains a lot of sediments, small pebbles, and when they are in the ice, they are moved by the ice and they will start grooving the beds. This is one example from the Spartan Solution Laboratory. What you have here is a rock. What you have there is the ice. So the ice is above the rock. And we observed that as the ice was moving, this rock was leaving these marks, white marks. And this is abrasion. This is this rock grooving, eroding slowly the bedrock. And it left, this very nice landscape here. Abrasion is like a sandpaper, huh? Just to make it understand, it's like you have a sandpaper and like wood, you can remove it by friction. Being faster, you erode more. And this is kind of the concept in the model based on early 1979, is we have this EA, which means erosion rate for abrasion, and it's dependent on UB. UB is the sliding, how fast does the glacier move at the bed. And then there is a couple of parameters, because CA, for example, it's a parameter for glass and bedrock hardness. In one way, what it contains, this parameter, is how thick is your sandpaper. Do you have a fine sandpaper, a thick sandpaper? And it also contains the resistance of the bedrock to erode, to erosion. And then we have L, which is a parameter set to 1 or 2, and we're going to discuss that there are some new evidences that this can be debated. And so 1 would mean that you have erosion rate proportional to ice velocity, and it would be linear. If you take L equal 2, you will have this parabolic shape. And you see this can change a lot, the erosion rate at the end. This abrasion, due to this concept, means that it will produce very fine sediments. That's one thing, and that's what we also observe in tills. The other part is scoring or cracking. Abrasion usually occurs on the source side of the bed, and cracking on the lee side. Lee side is because there you have usually a steeper face, and you have rocks that are easily detachable and can be eroded. This is one example from England. You have the ice that flows toward you, and you can see this bedrock and how it is fractured. And this is due to cracking, and it forms these very big boulders. And the basis for quarrying is kind of a concept that was it was a bit maybe tough to develop in a way. It's like people realize that when you have the bedrock here, because the ice is moving fast and it's not deforming, also it's moving fast but it's very viscous, it will go over some steps and it will not be able to close them because of the sliding. And this will open cavities, and these cavities will then left the contact between the ice and the rock at very small areas. So you can see that what's going to happen is the ice, the overall column of ice, all this pressure is going to be concentrated on very small points, and this will cause the rock to fracture. You will have a crack that will grow, and it will break off blocks that will then be eroded taken away by the ice. There is two models two papers that looked at it and discussed how do you get the crack growth and how do you compute this stress concentration and what does it depend on. I have to say I like equations because it really condenses our understanding of the processes. And so again, we have this erosion rate and the quarrying, and you can see again, like erosion, that sliding is present. So it's really an important thing that I will also bring later. And then we have some geometric parameters, so how long the spacing between two cavities, the height of the steps here that are here, HBS, LBF. What you don't see here is SBC is dependent on two things. So the sliding, because if you slide more, you will open a bigger cavity, and water pressure, and that's a new thing. is suddenly erosion becomes dependent on water, the hydrological system. And this is important because the more, if you have a lot of water pressure, you can open the cavities much more. And I will show you an example on that. A good thing, what's nice is also Barron brings, explains why do we observe big boulders, big rocks in tills and moorings, which are sediments at the front of ice sheets or glaciers. The problem is it's a model, but we need proof, we need to confirm it. And this is a very clever experiment organized, made by Denis Cohen et al. At the Svartis Institution Laboratory. And what they did is they built this case, and on top they placed a piece of granite. And in this granite they had a they cut a small crack on this side. And what they did is they placed this case and block at the interface between the bedrock and the ice. Because at this lab we can access the glacier bed. So you have to imagine that this part here was flush with the bedrock and the ice was on top. What happened is they could control the water pressure. So from here there was a small input and they could inject water and control the water pressure. And what they observed is when it was under the ice, they could form a cavity on the east side of this granite. And as the cavity was forming, they were measuring the activity of the crack. And that's what you see is, so the block in the cross section and the activity here, how much is used to acoustic emissions. So the crack growth is represented by each dot. And you can see that at the beginning, just below the crack, it started to have a lot of activity and the crack was propagating. And then they kind of could have controlled how fast this crack was growing by fluctuating the water pressure. And eventually, these acoustic emissions were much further down. And when they recovered the block, this part here was eroded, plucked away. So it really confirms this relationship with water pressure. Another important part, so then it's true for hard bed and soft bed, but it's more important for soft bed. So we look at the interface between the rock and the ice on top. But sometimes between the ice and the bedrock, you have big, thick sediments. And glaciers can erode them. Because in some conditions, so they are several, but what's going to happen is below the ice and in the sediments you have water, and this water, for some reason, will start to freeze on. So I can use some words like something supercooling. The way the water flows, suddenly it will have to freeze on because it doesn't have energy to remain liquid. That's one example. And so this water that is contained in sediments can freeze on below the ice, but it can also freeze on between sediments. And somehow, as these icelands grow, it will connect to the beds of ice, and these sediments will then be moved, transported by the ice. Again, we need observations to confirm this model, and there have been observations from Antarctica when they drilled boreholes from the surface to the beds, and they could see these layers of rocks, and they could see that these ice lenses and these freezing on as creating a very particular crystal size and characteristic that is they could observe it, confirming this idea. And again, from the Svartis Institution Laboratory, some people observed that too. And what they did is they went below the glacier, opened the cavity, put some sediments in a small trough, and then the ice closed, and after a couple of weeks they came back. And what did they observe? So you have the ice here, and you have in this area the sediments that they placed. And interestingly, the bedrock, they had painted some glass, and this glass got taken into the ice, and the ice soul was originally here, but when they came back, it was down there. So all these sediments were now frozen with the bed and eroded over time if there was some more sliding. The last one I want to talk about is something that happened in the year 2000. It was known before that if you look at sediments out of the glaciers, the mineral composition, there was a lot of ions and a lot of carbonates and bicarbonates, calcium and bicarbonates. And from the glaciated terrain, you can also observe a lot of these small deposits, and it's a carbonate deposit, like a limestone. And this is due to some key reactions that are occurring under the glacier where you have water. So you have water here. There is you have some CO2 here. CO2 with water gives you this. It's big, yeah, I'm not sure exactly, bicarbonate, I think. And this is acid, carbonic acid, sorry. And this acid can react with the rocks. S means solid. And it will take the calcium away and leave it and bring it to the sediments, to the water. And then you obtain this bicarbonate. So it's a way to erode by taking minerals. There is also the silicate factories that will produce potassium ions. And something a bit spectacular is sometimes when you go on the glacier in some areas, you smell eggs. You're like, well, what's happening? And these eggs this smell, is coming from the glacier bed, from below. And I will explain you why do we have these sulfates and there. And there is one famous example, which are the blood falls. So in Antarctica, coming out of nowhere, you have this water completely red. And I will explain in a minute why do you have that and why is it important. Because we have a problem. These chemical reactions, the major one that I mentioned before, they would happen very slowly under the glacier because the environment is very cold. And it requires added energy because of the thermodynamics. And the solution is people realize that in this water coming out, there was lots of microbes, lots of life. And these bacteria actually act as a catalyst, and they can speed weathering up. So, and that's the way you can chemically erode glaciers. Bacteria lose these reactions that I presented to you before. These bacteria can also play a key role in CO2 which can also be used by chemical weather. Just a side note. Oh, wrong one. Thank you. Java updates, my favorite. So let's look now at the topic, erosion rates. What are the controls? And who form this landscape? And by looking at the controls, we can then explain some of these variations, variability that we observed before. One thing is the geology. Something that maybe makes sense straight away is if you look at different lithologies and different rocks, maybe you erode more or less. And so, Cameron and what was the opponent you had, Heidi? Neil Glasser, looked at these rocks and looked at features that would tell us, do you have more erosion or less erosion? And the dots here represent the different types of rocks that they observed in northwestern Scotland. And what you have is a plot with the hardness of the rock and then the spacing between joints, because in the rocks you have fractures, sometimes that are repetitive, and so it means that you have a lot of joints here and very little hardness. And then large joints, much the joint is more spaced and thick rock. And what you see is when you have a lot of joints and very thick, tough to erode rock, they think that they observed that there was more evidence for that quarrying or plucking was dominant. Whereas if you were looking at rocks that are very little joints and very soft, it was abrasion that was dominating. So that's one way of explaining the variability in erosion rates. You can then look at the ice dynamics, and I've shown you the equation before, and we know that basal sliding is really an important thing. But there are other steps, like the basal thermal regime. It means, do you have the glacier bed or ice sheet bed? Is it temperate? Do you have water? Or is it cold-based, completely frozen to the bed? Then I'm going to quickly look at the ice thickness that influences the basal sliding, and then basal sliding and a particular phenomena surging. Because something that's not maybe, as I mentioned, that glaciers erode a lot. They're really major. But sometimes, actually, ice can protect the bedrock from erosion. And this is a study from Andre, who was studying at Finis. And what they did is they went to Svalbard and went to all the peaks here, and they look at some cosmogenic nuclei. It's a way of dating. When is the last time did you have ice or something covering the surface of the rock? And you can look at some component mineral like the beryllium, and this will tell you, so when was the last time, when was this rock last time eroded or covered by the ice? And the interesting part of the study is that they realized that the ice could protect for 1 million years these tops, and these tops have not been eroded at all. And that was the output. So this is a schematic of the understanding. So before the meat-based ocellates, 718,000 years, you had what they think is the whole Svalbard landscape was eroded at that time. But after, because in the places and we had more glaciations, the ice was covering the tops here and protecting, armoring the ice. That's one thing. But, so I mentioned before, but our regime is controlled by the thermal regime and not sliding, although it's a bit late. There is a study from Cobestal, and they looked at a range of glaciers covering a wide span of temperature, air temperature, but having the same climatic conditions. And they looked at the segments in front of these glaciers to assess the erosion rate. So you have some in the Antarctic Peninsula and in Patagonia. And what they observed is, I mean, you still have some erosion between, so here we are looking at sliding velocity on the y-axis, on the x-axis, and on the y-axis we have erosion rate. I forgot to mention before, this is logarithmic scale. Huh? This is very important. We pass from 0.01 millimeter per year to millimeter per year. And these glaciers that are in the Antarctic Peninsula, they are polar, most likely cold-based. And so their motion is mostly dominated by the ice deforming, not sliding. And you can see that the thermal regime and the presence of water was really increasing the erosion rates for glaciers that are close to Patagonia and reducing some of them close to the Antarctic Peninsula. So let's go back to basal sliding, this relationship between erosion and erosion rate and sliding. There is this very, very interesting study from Ehrman in 2015, And they were the first ones to manage to get a real measurements of sliding over a year and at different elevations, and they could relate this elevation to the sliding. So this is Franz Josef Glacier here, and this is the surface velocity, so the ice is approximately here. And due to the lithology, they could detect where, so they were looking at the discharge of the glacier front, and looking at the sediments that they were collecting, they could see that some of the sediments had properties of the rocks very close to the front, and sometimes, and as they were, and they could see that some sediments were coming from further up, and they could, at the end, look at how much sediments do you have per section of the glacier, so further up. So what you see is this black line, which means that we have erosion rate proportional to sliding, and L equal 1, is not true. And it's all and the problem is that a lot of models are using this L equal 1. And so what they observed is it's more like a nonlinear erosion, because this ice velocity, so at the fastest, that was not linear. That's one important thing. L equal 2. It's kind of the controls this basal sliding. How does it make vary the erosion rate? This is kind of a spectacular video of surging. And surging, it's a phenomenon where the glacier will accumulate some mass, and suddenly, because of a threshold, it will advance and go into the fjords, and these surges will move mechanically the rocks in front of their fronts, but they will also squeeze the basal sediments when they have fractures, because when the glacier surge, you have lots of fractures, it's really broken up, and because of this pressure, the advance, the sediments will be squeezed in. And I want to show you one example. It's from a surge of variegated glaciers in Alaska. It's from that was quite old. So variegated glaciers. It's a time-lapse camera. So you have the glaciers here, and they left the camera at the front. And what you will see now is the glaciers suddenly will surge. So you see that the surface is going up. So first the glacier goes up, and then it will advance. And if you look at the sediments here, and you will see how much they are pushed and squeezed, and that's when they are eroding. So you see, so it has been the mass, then it moves, and you can see the sediments taken even on the surface, on the glacier surface. Luckily, they removed the camera before it was taken away the ice. But so unfair environments, when they looked at the discharge in front of these glaciers, they nearly saw like 30 centimeters sediments eroded nearly in 2 years. See, up to 30 centimeters, and that means an erosion rate of 150 millimeters per year. So something also to take into account. I showed you this landscape formed by glaciers, and I mentioned these hanging valleys. And how come if you have valleys that, if you have rivers, they are more or less having the same elevation when they meet? But why do you have this huge peak here? And this is due to the erosion rate. When you have two glaciers meeting to each other, something is happening. And this something is shown by this model study from Macro et al. So here is the cross section, you have the elevation, you have distance, and then you have this integrated ice discharge. So what you see here is they included a tributary glaciers. These glaciers are just beside, and they had the main trunk in front. So this is 2D, but you have to think it's a 3D process. And what happened is when they included distributory glaciers, the ice from these older glaciers, increasing the ice thickness where they were meeting, and increasing the ice discharge, and thus increasing basal sliding. And by increasing basal sliding, you were starting to form this small step in the bedrock. And that's a way of causing this very steep cliff hanging valleys. And you can also explain that this over deepenings. I mentioned it's very big trough with, filled with sediments, and that's the way to see it. When you have two glaciers meeting to each other on the downstream, because suddenly you have more ice, you erode more, and you form this trough. Now, distributional hydrology, kind of my favorite topic, what we're going to talk about later today. We're going to talk about these cavities. So we have this equation with erosion rates for quarry, and I mentioned that we have these open cavities, and they are related to water pressure. What you have here is kind of a cube, if you look below the glacier. So then you have the ice, and then between the ice and the bedrock, because water from the glacier surface reaches the beds through crevasses, it will flow at the bed, and it will form these channels. This is one channel, and these cavities, and they are linked to each other. And this, what's important is the water will create this. Sorry, I just 1, 2, 3. This drainage system will affect the pressure, the water pressure, and this will then affect the erosion rate. It's a bit complex. We're going to talk about it a bit more this afternoon, but it's this system, how it looks like, how it is, this characteristic that will control the effective pressure, the water pressure. And I want to show you a model version, and it's interesting because models help us also combining two theories. We have the erosion rate from abrasion, from quarrying, and this model includes them both. And what you will have here is you have the abrasion on top, the erosion rate of quarrying, and then you have the effective pressure. And effective pressure is the ice pressure with water pressure. So if it's getting close to 0, it means that you have a high water pressure. And you see already the problem from before, N equal 1, when maybe it should be N equal 2. And this is for a distributed drainage system. So what this person did is he looked at the seasonal evolution. So in a season, in summer it's warmer, you produce water. The water goes to the bed and it changes the water pressure at the glacier bed. And so what's happening is here you have melt. I think it represents melt here. And what you have here is, because you have water pressure, you increase the sliding, and you will see the friction of the bed. And because you increase the sliding, the abrasion is increasing here. The problem is the drainage system is very efficient when there is lots of water, and it means that quarrying is actually limited to the upper part. That's one thing. And then the final slide about the hydrology is to look at what if you don't include sliding, hydrology is water, and this is just a result again of a model, but it kind of shows what happens if you don't include it. So you have a mountain range that is caused by eroded by fluvial processes at the beginning, and then what they did is they grow glaciers, and that's the difference when you have river and suddenly then you grow glaciers and it will erode. And you see what's happening is the valley widens, and gets deeper. And this is without including the hydrology. Then see, when we include the water, and this water is increasing the sliding, and what you see here is a much deeper valley. And you can really recreate these hanging valleys also that I was mentioning before as they merge, tributary merge together, and then this added phenomenon caused by the hydrology, superficial hydrology. If you look at hydrology, then you have to think about where do you have melt and where you don't have melt. Because then what you did here also is you steepen this area. Because above here, maybe you have less melt down there. It's called the equilibrium line altitude, or the snow line for remote sensing. It's then above you have less water coming, and below you have more water. And that is changing a lot the erosion rate, and so the shape of our landscape. So, short conclusions. I hope you've understood, and I've shown you that glacier erosion has formed a large part of our landscape, and is much more efficient than fluvial processes in the high mountains. You have 4 processes that you should remember. The abrasion, quarry, they are the most important ones, the one that we understand the most. And then we have this diluent treatment, so when we have sediments, it's very common in the ice sheets. And then we have this chemical weathering, which has this very interesting relationship, connection with the subglacial life, so biology. And then, to answer the final title, final question, so what are the processes that control glacier and sheet erosion rates? I hope you've been able to see that rock geology is important, although I would say now that it's not maybe as important as the ice timelines when you look at the overall landscape. What's important is more the basal thermology, because it can actually protect or erode more. If you have cold base, you protect. If it's warm base, you erode. Then we have basal sliding, very key point. And I hope you've understood that superficial hydrology is something that you should never forget, because it controls a lot the erosion. Thank you very much.
Thank you very much, Pierre, for your presentation. So this session is now over, and we'll meet again. Hope we'll see most of you 1:15 for the official presentation ceremony.